stereo mirror, et cetera, specific location. There's a list of them there on Blackboard, and also a helper philosophy that's on there that you can work with because there isn't one in your book. And then chapter 10 is on NMR, and the bulk of that would deal with interpreting hydrogen and carbon NMR spectrum. Not on the theory of NMR, because that's not what we're doing here, but on where the power is in NMR and how it does and doesn't work. I mean, no technique is perfect, but NMR has a lot of unique features, and that's what we hope to present. We will subsequently look at two other forms of spectroscopy, infrared spectroscopy and mass spectrometry, and the combination of NMR, IR, and SPEC is what's particularly powerful, because as you'll see when we get through all three of them, is that they all complement one another. The kind of information we get from one doesn't duplicate, but adds to the kind of information that you get that's from another technique. So we'll get back to that. So just check that email if you haven't done that already, and if your email's not working, get it working. You can't survive here with a mailbox that's overquoted. If your mailbox is full, clean it out. If you don't have a computer or a smartphone to work with, there are computer labs all around campus, right in this building on the 5th floor that you paid for. So feel free to use that, but get yourself plugged in, because all of the information that you need, not just from me, but from the registrar, from financial aid, from everybody, comes through email now. They don't send anything out by paper anymore. Okay, so we've been talking about hydrogen in NMR. Anyone have any questions on that before I continue with it? Okay, we're ready to start looking at some spectra, but I have to give you some clues in terms of this last category of information that you get from HNMR. And there are four main categories of information. You have the number of resonances, whether they're singlets or doublets or triplets, tells you how many chemically different types of hydrogens there are. The areas underneath the peaks tell you the relative numbers of each types of hydrogens. If you have spin-spin splitting, it can give you neighboring information, like is this CH3 next to a CH2 or a CH, or no chemically different neighboring hydrogens at all. And the fourth piece of information is where those resonances are, which we call the chemical shift. The NMR spectrum in hydrogen NMR is actually a very small window runs from 0 on the right to 10 on the left. Virtually all of the common chemical types of hydrogens appear in this 0 to 10 window. And it's a linear scale, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The units are a little strange for a spectroscopic technique in parts per million. You don't need to worry about that. It's just a linear scale. The parts per million unit is there because you're really looking at frequencies that differ from a reference frequency by a few parts per million. Like 1 megahertz out of a million megahertz would be 1 part per million. But it is linear, and everything that you need to see is in this window. Now, what can you predict will appear in fairly reliable places throughout this window? Well, it turns out not a lot. Chemical shift is the weakest of the four pieces of information, but students really gravitate towards it because it's the easiest piece to use. But don't overdo it. not too many different kinds of hydrogens that you run into. If you have hydrogens on a saturated carbon and they're attached to another saturated carbon, and that could even be methane, of course, but you would never analyze methane by NMR. Those kinds of most common saturated carbon CH hydrogens that are next to nothing unusual other than other saturated carbons and hydrogens, those appear at around 1 ppm. So if I put methane here, that type of hydrogen, but it could be like a CH3 in ethane, or a CH3 in methyl cyclohexane, or a CH2 in propane. Those kinds of ordinary run-of-the-mill default, very stable carbon hydrogen types are around 1 part per million. Now you sometimes see a peak at 0 because there's a reference standard whose hydrogens do appear by definition at 0. All of these ppm values are actually relative to wherever the hydrogens for this compound happen to appear when you take the NMR spectrum. Now, that's fairly carefully controlled, so it almost always is exactly at 0, but this is tetramethylsilane, or TMS. It's a volatile, very stable organic liquid that is added to NMR solutions when you run an NMR spectrum. Now, just quickly to tell you how you make up an NMR solution, it has to be in solution where you have a dilute solution of your sample and a special NMR solvent. The most popular NMR solvent is chloroform or trichloromethane. Now, we don't use chloroform itself because we don't want this hydrogen to appear so we use about 1 mil of chloroform and about 20 milligrams of the sample. So the solution, once you dissolve the sample, is mostly chloroform. That would mean that when you look at the HNMR, the hydrogen for chloroform would appear as a humongous peak, and probably you wouldn't even notice the peaks from your sample. To get around that, we use a derivative of ordinary chloroform where the hydrogen is replaced by deuterium. It's called deuterated, D-E-U-T. Remember, deuterium is the H2 isotope of hydrogen. Deuterium is active in the NMR, but at a very different frequency from ordinary H1 hydrogen. So you don't see the signal from deuterium in the hydrogen NMR. It's as if you didn't have a solvent at all. So when you look at the spectrum, you see just solvent, you see just sample, plus a tiny peak for this additive that's put in there to set the scale. So wherever the 12 equivalent hydrogens of tetramethylsilane are, that's considered 0. And this is a sensible standard because the carbon-silicone bond is polarized where silicone is less electronegative than carbon, and that piles up electron density around the carbons and the hydrogens. Now, one of the main reasons, but not the only reason, that hydrogens appear at different places in the NMR spectrum at different frequencies is because the electron shield, as we call it, around the hydrogen acts like a deflector for the magnetic field. The same way your cell phone loses its signal when you go by a large building with a lot of steel in the structure. The magnetic field at the nucleus is diminished by the electron cloud around the hydrogen. So if you have two hydrogens and one has a thicker electron cloud than the other, the magnetic field is slightly weaker at that shielded hydrogen nucleus. So high electron density causes hydrogens to resonate at a slightly lower frequency. If you lower the magnetic field, you lower the energy gap, and you lower the frequency necessary to make the spin jump. So TMS appears at a lower frequency, which is really what this scale is, than any of the other normal types of hydrogens in organic compounds. So it's a good standard in that it's pushed to one side and doesn't get in the way. You wouldn't want a standard that pops up in the middle and possibly obscures some of the hydrogens in your sample. It's also volatile and inexpensive and harmless, so it's a great standard used worldwide. So that's 0, and you may see a peak there, but it's not part of your sample. Anything else is. Okay, so, and by the way, chloroform, you actually take a spectrum of chloroform. That hydrogen is at 7.25 parts per million. Very far away from methane at 1 ppm. The reason it's so far away is because these chlorines, which are electron withdrawing, are thinning out the electron cloud around the hydrogen. So that hydrogen is not very well shielded by the electron cloud. That means that this big, fixed, superconducting external magnetic field, most of it is getting into that nucleus. So that hydrogen has a particularly strong magnetic field and a particularly large gap in energy between the spin states, and so it flips at a higher frequency than the hydrogens in methane. This is a very important concept with chemical shifts, and that is electron withdrawing groups around the hydrogen push the peak to the left. If you look at chloromethane with one chlorine, it shifts it a little bit to the left. If you look at dichloromethane, it moves about to the middle of the spectrum. And if you look at trichloromethane, it moves to about 7. So the incremental jump from each chlorine is almost additive. It's a very predictable effect. Electron withdrawing groups always expose the hydrogen and cause it to resonate at a higher ppm value. So what would be, let's see, example of that would be another type of hydrogen is a hydrogen on a carbon that's right next to a carbonyl. Carbonyl groups are electron withdrawing, like a chlorine. The carbon of the carbonyl is electron deficient because the oxygen is pulling electrons away from the carbon. So the whole thing is causing a de-shielding effect, and that moves the hydrogens down to around 2 parts per million. Now it doesn't have to be a CH3, but a CH next to an electron withdrawing group like a C double bond O, or a Cl, a single Cl, or a Br, or an O. So one electron withdrawing group, and it does matter whether it's C double bond O or chlorine or bromine, but not a lot. So any electron withdrawing group very, very close to the hydrogen would cause it to shift to the left, somewhere around 2 or 2.5 ppm. Now that's a lot of kinds of hydrogen. In fact, there's pretty much a blind, almost unintelligible jungle in there between about 3.5 and and 1.5, where it could be almost anything causing that little incremental shift to the left. But that's a big clue. So if you see a resonance at 2.2 parts per million, that is not a normal saturated CH next to only other saturated carbons and hydrogen. There's something causing that incremental shift, and it's an electron withdrawing unit, like a single chlorine or a bromine or an oxygen or a nitrogen or a C double bond O. So a lot of hydrogens appear in that region. And again, you can't tell whether it's CH next to a chlorine or an oxygen or whatever, but you can tell that there's something there. It's not a regular methane type hydrogen. Around 4, there is a particular kind of hydrogen that is very common in organic molecules, and it's part of the ester functional group. That type of hydrogen appears between 4.5 and, say, 3.5. Now, I'm not going to drag you through all possible things. I'm just trying to give you some clues that will help you to use the chemical shift to get some answers. And I mention this because one of the common dilemmas that you get into is, let's say you have this. Okay, good question. Esters look like this. This is the what they call the ether oxygen of the ester, and this is the carbonyl oxygen of the ester. So the esters have two different oxygens. There's a carbon attached to the ether oxygen, and a hydrogen on that is close to 4 parts per million. Now, what I put up on here on the board are 2 isomeric esters. This one is the methyl ester of propanoic acid, and this is the ethyl ester of ethanoic acid. Now, by NMR, these 2 compounds would appear hard to distinguish. How many chemically different types of hydrogens in each? 3. The relative areas would be, you'd have 2 of them with 3 hydrogen area and 1 with 2 hydrogen area. Same for both. In terms of the third piece of information, spin-spin splitting, how would this CH3 appear? Triplet. What about the CH2? That's a quartet. And what about the CH3? Singlet. So there's a 3 hydrogen triplet, a 2 hydrogen quartet, and a 3 hydrogen singlet. And you can see here, the bottom one has the same thing. So, of the 4 pieces of information, 4 categories, 3 of them are indistinguishable. They both have 3 chemically different types of hydrogens. The relative areas come out the same, 2 with 3 and 1 with 2 relatively. And the spin-spin splitting patterns are all the same. Quartet and a singlet and a triplet. The only way you could tell these 2 apart is by the 4th chemical shift criterion. Let's think about that. 3 approximately appear based on what I've said? Around 1. That's a CH3 attached to a CH2. This electron withdrawing effect falls off very rapidly with distance. I want to emphasize that. So if you look at ethyl bromide, for instance, the CH2 that's right next to the bromine is shifted to about 2 parts per million, but the CH3, which is only 1 more bond away, those hydrogens don't even see any effect from the bromine. So this falls off real fast with distance, this electron withdrawing effect through the single bond. So this is about, and we're being approximate, about 1.0. This CH2 is right next to the C double bond O. Where would that be? Just roughly. Around 2. And this C double bond O, OCH is this type right here, which would be around 4. Approximate. To go to this one, and assign those rough approximate chemical shifts, now you can tell the two apart. If you had a spectrum of just one of them, with the top one, the CH3 singlet would be around 4 because it's an ester type of CH. And the CH2, which is a quartet, would be around 2. In the bottom one, the CH3 singlet would be around 2, and the quartet would be around 4. NMR is particularly good at distinguishing isomers because it gives you a lot of intimate details, but you have to be able to read it. In this case, the deciding factor would be the chemical shift. In some other case, it might be the spin-spin splitting. Yes?
Oh, it's, like, why is it that two methyl groups are different in terms of the resonance?
There's a where the chemical shift.
No, like, why is the left methyl group single, a singlet?
Spin-spin splitting. Spin-spin splitting is caused by the presence of chemically different neighboring hydrogens. This CH3 doesn't have any chemically different neighboring hydrogens. This one does. So this one is split into N+1 lines by the 2 chemically different neighboring hydrogens. Same here. So the 2 CH3s are quite distinguishable, not only by chemical shift, but by the spin-spin splitting. You know which one is which. Okay, that's just an example. To extend this then, where else can we go? Well, between 5 and 6, you have hydrogens on a carbon-carbon double bond, an alkene type, simple alkene type of hydrogen, like 1 propene. Then, between 7 and 8, you have a very important region that corresponds to hydrogens on a benzene ring. The benzene ring is it's probably the most stable chunk of carbons in any organic molecule. Benzene is the most famous grouping in organic chemistry. There are 2 whole chapters on it in Bollard. It's so important. That appears in a lot of compounds, so you have to watch out for that. Now, it is actually quite easy to recognize when you have a benzene ring because virtually nothing else has hydrogens between 7 and 8 parts per million. Now, that's not a simple electron withdrawing effect. That's a complicated effect that has to do with circulating electrons and induced magnetic fields. Chemical shift is a lot more complicated than just electron withdrawal. But that is one of the major factors in chemical shift and the easiest to deal with, and we're not going beyond that. But for a particular reason, hydrogens on a benzene ring are clearly between 7 and 8. The other way you can tell you have a benzene ring is if you do a degree of unsaturation calculation on the formula. And you find that there are at least 4 degrees of unsaturation. If you have a small molecule, say less than 10 or 12 carbons, and you have 4 degrees of unsaturation, you can be almost guaranteed that 4 of them are from a benzene ring. 3 from the 3 pi bonds, and the 4th from the ring. So all by itself, a benzene ring is a whopping 4 degrees of unsaturation. Nothing else comes even close. That's about the most unsaturated things can get. And the last thing is between 9 and 10, there is a unique type of hydrogen that appears there, and that's the aldehyde type of hydrogen, where the hydrogen is directly bonded to the carbonyl. And that unusually large chemical shift, again, is not due simply to an electron withdrawing effect. It has to do with a what's called diamagnetic susceptibility in the electron cloud. So read about it. It's not that complicated, but that's not simple electronegativity, so you have to kind of memorize those. This is a dead giveaway between 9 and 10 for an aldehyde, 7 and 8 for a benzene ring, and around 1 for saturated. The stuff in the middle is a little murkier because it's very crowded. So don't rely solely on chemical shift. Even in this example here, where it comes down to chemical shift, you would first try to do it by how many types of hydrogens, spin-spin splitting, and areas underneath the peaks. If you come up dry, then you have to pay a lot of attention to the chemical shift. There are whole books that contain nothing but chemical shift tables. So if a peak is at 2.65, you can narrow that down to a particular type of hydrogen, but it's risky. Chemical shift depends on temperature, it depends on concentration, and it depends on the solvent, which normally is CdCl3, but we have other deuterium solvents that we use, like D6 acetone, or D4 methanol, or D3 acetonitrile. There are a bunch of other solvents, and chemical shifts move around in those solvents. The one thing you can't pin down with any certainty at all is an OH. OH chemical shift is very, very variable. It can move all over the place. So it's kind of risky to try to identify an OH in HNMR. The most you can do is make sure that it integrates for the area to 1 hydrogen. And sometimes when all your peaks are short, like this, it will be characteristically broad or uncharacteristically broad. That's because hydrogen NMR, in hydrogen NMR, the hydrogens exchange from one oxygen to another. I need to get to this now.